Today I will discuss about iterative circuits. Okay, what is iterative circuits? See, number of identical cells are arranged in a regular manner. This is called an iterative circuit. In an iterative circuit, we have a number of cells and that are arranged in a regular manner. Arithmetic operations like addition can be implemented with the iterative circuit because same operation performed on each pair of input bits. See, in these iterative circuits we can implemented for an arithmetic operation like addition, but that means a number of bits are bits addition. Okay, each bit is added to corresponding bit. That means this can happen within each cell. Okay, for example, this is cell number 1 2 3 like that, n cells you have. So two things comes. This is the previous carry, this is the input, and carry input to this are added, you will get the result output like that. So anything which are identical cells are, say the operations are identical, we can arrange it in a regular manner. Okay, addition means consider a 2-bit addition or 3-bit addition. Bits are adding, same operation happen in each and every cell. Okay, so that can be arranged in a particular manner. Such a type of circuits is called iterative circuits. The structure makes it easier to fabricate in IC form. That's why we choose iterative circuit. Why? Because this structure makes very easy to fabricate in IC form than circuit with irregular structure. This circuit can function as a parallel input, parallel output device. Okay, so look at here. This is the design of comparators. For an example, here I am considering comparator design. Okay, iterative circuit is nothing but number of identical cells are arranged in a regular manner. That means if you need a particular operation, if the same thing happens on each and every cell, then that cells can be arranged in a particular manner and clubbed together to form a circuit. This is very useful for if you want to fabricate these things in IC. In this type of conditions are very useful. How to design? For example, I am taking a design of a comparator here. Okay, comparator means what? An input comparator. Here I am drawing an input comparator. Okay, what is comparator? Consider these two bits A and B. We need to check whether A is, only three conditions are there, either A greater than B or A less than B or A equal to B. Three conditions are there. Here I have a bit. This is 3-bit, 1, 2. This is a 4-bit. This is also a 4-bit. This is A, this is B. By looking itself, we can understand whether which one is bigger. How to identify? We can identify that A is bigger than B. Okay, but how the machine will identify which one is greater, which one is lesser? That's the point here. Okay, how the machine will identify? Okay, look at here. Here A is 1011, B is 0111. Two ways we can identify this, either in left direction or either in through right direction. Okay, suppose here the leftmost bit, look at this. In one way we need to scan from left to right. Okay, which one is bigger, like that. First the machine will check these two bits, these two are equal, then he will make a decision that A equal to B. Now consider the second bits, A equal to B. Now consider the third bits, B greater than A. Now consider the fourth bit, A greater than B. So what is the final net outcome? A is always greater than B because this bit is bigger. But if we scan from left to right, we need to scan first 3 and the fourth scan. After reaching fourth scan only we can identify which number is bigger. Okay, നമ്മൾ ലെഫ്റ്റിൽ നിന്ന് റൈറ്റിലേക്ക് സ്കാൻ ചെയ്യുമ്പോഴുള്ള പ്രശ്നം, ഈ ഓരോ ബിറ്റും നിങ്ങൾ സ്കാൻ ചെയ്തുകൊണ്ടേയിരിക്കണം. അത് അൺനെസസറി ആണ്. കാരണം എന്താ, ഈ ലാസ്റ്റ് ബിറ്റാണ് ആക്ച്വലി എം എസ് ബി വിൽ ഓൾവേസ് ഡിറ്റർമൈൻ വിച്ച് നമ്പർ ഇസ് ലാർജർ. ഓക്കെ, എം എസ് ബി ആണ് തീരുമാനിക്കുന്നത് ഏതാണ് വലുതെന്നുള്ളത്. അപ്പോൾ നിങ്ങൾ ഇവിടുന്ന് ഇങ്ങോട്ട് സ്കാൻ ചെയ്ത് വന്നു കഴിഞ്ഞാൽ കാര്യമില്ല എന്നല്ല ചെയ്യാം, ബട്ട് that is unnecessary scanning. But if you check from right to left, with a single scan you can identify which is greater. How first the machine will scan the MSB. This is A is 1, B is 0, so A is greater than B. Then from the first scanning itself we can understand this is greater than B. So we made a conclusion that A is greater than B. Okay. So this is the idea. അപ്പോൾ നമ്മൾ റൈറ്റിൽ നിന്ന് ലെഫ്റ്റ് എടുത്താൽ മതി. സ്കാനിങ്ങിന് എളുപ്പമാണ്. ഒറ്റ ബിറ്റ് സ്കാൻ ചെയ്താൽ മാത്രം മതി. എയും ബിയുടെയും MSB സ്കാൻ ചെയ്ത് ഏതാണ് വലുതെന്ന് നോക്കുക. So if A is greater, then no problem. If both are equal, then there comes the problem. Okay. If both bits are equal, what happens? Consider this example: 1 1 0 1 0 1 1 1. Here, if we go from here to here, first both are equal. This is A, this is B. Here both are equal. Then you need to check for the second bit. 0 1. Here this is bigger, so we can say that B is greater than A. Like that comparator compares. So this is the comparator structure. N-bit comparator. I have n cells, cell 1 2 cell I, cell n, like that. So this is the output circuit. Z1 Z2 Z3. Z1 means x less than y, and that condition we call it as Z1. If x equal to y, that is Z2. If x greater than y, at that condition is Z3. This is the three conditions. This is the cell 1 for first bit. X1, Y1 are the first bits. See, this is X, I, Y. Okay. This first one is X1. This is X2, X3, X4. This is Y1, Y2, Y3, Y4, like that. So first we need to compare these two, that is X1, Y1, or Xi, Yi. If we choose this cell, it is Xi, Yi. Okay. So first bit is X1, Y1. This is X1, this is Y1. We need to compare these two. And what is A1, B1? A1, B1 is the present state of this. Okay. Suppose you are considering these two are the Xi, Yi, 0, 0. At that time, what is the present state of this cell? This is the present state. Okay, like that. Present state. This is the next state. For considering the cell I, AI, BI is the present state. Next state is AI plus 1, BI plus 1. Xi, Yi is the inputs. Clear? So this is the output. Now we need to draw the truth table, state table for this comparator. This is the state table. Present state, next state, output. What is the present state? Si. Okay. Suppose the present state is stored here. I told you this present state of which state is stored here. If both are equal, x equal to y. If one is greater, means x greater than y, or y greater than x. Like that conditions are there. This is the present state. Next state, outputs. So first this present state is I represent as Si. Next state is Si plus 1. Suppose the present state of a cell is x equal to y, or x greater than y, or x less than y. Like that the present states. Inputs Xi, Yi are 0, 0, 0, 1, 1, 0, 1, 1. Okay. What are the output? Z1, Z2, Z3. Z1 is what? I told you Z1 is x less than y, Z2 x equal to y, Z3 x greater than y. Okay, like that. Look at here. Here Si, initially it is x equal to y, that is a condition. X equal to y is the present state. 0, 0 comes. 0 means Xi 0, Yi 0. Both bits are equal. Here x equal to y I represent as S0, x greater than y is S1, x less than y is S2. If 0, 0 comes, what is the next state? S0 only. That means both bits are equal. X equal to y. That means both bits are equal. That it is represented by S0. S0. What about 0, 1? Both are different. And y is greater than x. Y greater than x means S2. That's why S2. this is 1 1. In 1 1 both are equal, so S0. This is 1 0. That means x is greater than y. X is greater than y, S1. That is S1 here. Similarly, what about for 0 0? Here it is S1. This is the present state. What happens if 0 0 comes? 0 0 means equal. Okay. 0. See, the condition here is, here x equal to y is the present state. So present state is x equal to y. What are the different combinations? And what is the next state? Here it is written that x is greater than y. Okay. The condition is like this. See, in the first case, x equal to y, that means this is the case, x equal to y, both bits are equal. Then we check for all other bits. But in second case, it is written that a is greater than b. A is x, is this is x, this is y, and x is 1 means x greater than y is 0, x 1. That means this is a is here, a is greater than b, na? For example, instead of a, I am writing it as x. This is y, so I can write it as x greater than y. Why? Because m must be is 1. So I don't need to check other bits. With any doubts, I can say that x is greater than y. Okay. അപ്പോൾ ഇത് നിങ്ങൾ സ്കാൻ ചെയ്യുന്ന സമയത്ത് എക്സ് ഗ്രേറ്റർ ദാൻ വൈ എന്നുള്ള കണ്ടീഷൻ വന്നു കഴിഞ്ഞാൽ പിന്നെ സ്കാൻ ചെയ്യേണ്ട ആവശ്യമില്ല, നോക്കേണ്ട ആവശ്യമില്ല, ചെക്ക് ചെയ്യേണ്ട ആവശ്യമില്ല. കാരണം എന്താ, എം എസ് ബി ഇസ് 1 ഫോർ എക്സ്. ദാറ്റ് മീൻസ് ദിസ് ബിറ്റ് ഈസ് ബിഗർ ദാൻ ദിസ് വൺ. വാട്ട് എവർ ഇറ്റ് മേ ബി ദ അതർ കണ്ടീഷൻ, യു ഡോണ്ട് വാണ്ട് ടു ചെക്ക്. Why? Because this bit is higher, so definitely x will be greater than y. So that's why for x greater than y, whatever may be the other condition, it will be s1 only. Why? Because x is greater than y, s1. So I put 0 0 comes means the present state 0 0 input comes. It won't check. Why? Because msb is 1 here. Msb is 1. That's why x greater than y. Okay. See, the MSB is 1 here. Now, whatever may be the next is, now x 0 0 comes, no need to check. It is inbuilt, it is written that x greater than y. See, 1 0 എന്ന് പറയുന്ന കണ്ടീഷൻ വരുമ്പോൾ എക്സ് ഗ്രേറ്റർ ദാൻ വൈ ആണ്. ഇനി അടുത്ത കണ്ടീഷൻ 0 0 ചെക്ക് ചെയ്യേണ്ട കാര്യമുണ്ടോ? ഇല്ല. കാരണം എന്താ, എക്സ് ഗ്രേറ്റർ ദാൻ വൈ. സോ ഇറ്റ് ഈസ് 1 ഉള്ളി. 0 1 വന്നു കഴിഞ്ഞാലും 1 വന്നു കഴിഞ്ഞാലും ഇതൊന്നും ഇതിനെ അഫക്റ്റ് ചെയ്യത്തില്ല. കാരണം എന്താ, എം എസ് ബി ഓൾറെഡി 1 ആണ്. എം എസ് ഈസ് ഓൾറെഡി 1. സോ ഈ ബാക്കി ബിറ്റ്സ് സ്കാൻ ചെയ്തിട്ടും കാര്യമൊന്നുമില്ല, എപ്പോഴും ഇതായിരിക്കും ഗ്രേറ്റർ. സോ എല്ലാ കേസിലും യു ക്യാൻ റൈറ്റ് ഇറ്റ് ആസ് എക്സ് ഗ്രേറ്റർ ദാൻ വൈ. ദാറ്റ്സ് വൈ ഇറ്റ് ഈസ് റിട്ടേൺ S1. Why? Because whatever may be the conditions, in the beginning present state is x greater than y. That means MSB is 1. So all bits are 1. Next state is 1. Here the condition is x less than y. That is S2. S2 I am writing it as S2. X less than y means, sorry, that means y is greater than x. That means second bit is higher. Here the condition changed 0 1 like that. 0 1 1 1 1 1. Here the MSB, this is y, this is x. Here this is greater. അപ്പോൾ ഇവിടെ y ആണ് ഗ്രേറ്റർ ആയിട്ടുള്ളത്. അപ്പോൾ പിന്നെ ബാക്കി ബിറ്റ്സ് ചെക്ക് ചെയ്യേണ്ട കാര്യമില്ല. ചെക്ക് ചെയ്താലും എന്ത് തന്നെയായിരിക്കും, ഇത് തന്നെയല്ലേ വരും. സി MSB y is 1. Now 0 0 check ചെയ്യുമ്പോഴോ no need to check. Why? Because MSB y is 1. So S2 is the bit y is greater than x. Okay, so S2 is the next state. Now what about Z1, Z2, Z3? Is x equal to y means Z2. So here x equal to y, Z2 is 1. X greater than y means Z3 1. X less than y means Z1 1. Now the transition table. In transition table put S0 0 0, S1 0 1 instead of S2 1 0. So write like this: 0 0 0 1 1 0. Instead of this S value you put these values here. Now you need to draw the circuit. For that you need to write the equation for AIBI like that. Here present state is ai bi. See, I am writing the circuit for this comparator. Here I am taking this cell. For n bit comparator I am designing the circuit. So what is the ai bi present state? xi yi input. Next state is ai plus 1 bi plus 1. What is the output? z1 z2 z3. So that's why present state is ai bi. Next state xi yi. For input xi yi, what is the next state? ai plus 1 bi plus 1. Output 0 0. Present state is 0 0. This you complete with this. Okay, instead of this value we can put this. Now to write equation for ai plus 1, we need two equations, ai plus 1 bi plus 1 and z. Oh, what about gamma for ai plus 1? We need to reduce the gamma. For ai plus 1, how to write the 4 variable gamma? Inputs are ai bi xi yi. What is ai plus 1? ai bi xi yi. What is ai plus 1? 0 0 0 1 1 1 1 0. Combination 0 term. So 0 0 0 0. What is that? 0 0 0 0. What is ai plus 1? 0 only. For 0 0 0 1, what is ai plus 1? Look at here. 0 0 0 1. What is ai plus 1? 1. Okay. Like that. For 0 0 1 1, what is ai plus 1? For 0 0 1 1, what is ai plus 1? ai plus 1 is 0. That means the first bit. Row first term on ai, second term is bi plus 1. First term ai plus 1, second term bi plus 1. Then first term, this second terms. So you fill up this table like this way and reduce it. You will get ai plus 1 as ai plus bi bar xi bar yi. Similarly, bi plus 1 is bi ai bar xi yi bar. Similarly for z1, this is for z1. This z1, how to write z1? See, look at here. Z1 is directly depends upon this a plus 1 and bi plus 1. Okay, so directly it is dependency is there. So z1 depends on an plus 1, bn plus 1. Okay, why? Because it is written there in the circuit, output circuit. Z1 is directly depends upon this, Z2 is depends upon this, Z3 is also depends on, what is this? A plus 1 bi plus 1. So Z1 is a plus 1 bi plus 1. 0 0 0 0 1 means Z1. Why? Because Z1 means x less than y greater than x. Here y is greater than x, so that's 0 0 0 0 1 0 1 0 1. Why 1 0? Look at the table. So for 1 0 we have z1 is 1 for 1 0. Okay, for all others z1 is 0 only. So for 1 0 combination z1 is 1, all others 0. 1 1 is not there, so don't care. So reduce this, you will get an plus 1. Now for z2, for z2 1 0 0 is the only one output combination. That's why for 0 0 it is 1, for all others 0, and this is don't care. So reduce this, z2 equal to an plus 1 bar into bn plus 1 bar. What about z3? z3 is 1 only for 0 1. Look at here, z3 is 1 for 0 1. z3 is 1. So 0 1 combination 1, all of this 0 and don't care. So solve this, z3 equal to bn plus 1. Now draw the circuit. You have all the equations. So what is ai plus 1? ai plus 1 is equal to ai plus bi bar xi bar yi. So you need ai bar bi bar xi bar yi bar. So ai plus 1 equal to bi bar xi bar yi plus ai. Now bi plus 1 equal to ai bar xi. Bi plus 1, it is written bi bar ai bar xi yi bar. So bi plus ai bar xi yi bar. So that is bi plus 1. Now what is for z1? Z1 it is an plus 1. So for z1 it is an plus 1. Like that it is etc etc this nth time. This for nth time. an1 an plus 1 direct to z1. Z3 is bn plus 1. Z2 is this an plus 1 bar into bn plus 1 bar. So it is written like this.